Okay, 9.6, solving right triangles. Your essential question. When you know the lengths of the sides of a right triangle, how do you find the measures of the two acute angles? So far, you've been given like an angle in a right triangle, and you've been able to use that to help you find a missing side. Now we're going to use, or potentially just be given, the three sides, and now we're going to have to find the lengths of the angles. Okay, so starting with example 1. Determine which of the two acute angles, remember, we've got one that's a 90-degree angle, so the other two are acute. So which of the two acute angles has a sine of 0.4? Well, in order to do that, I basically have to set up the sine ratio for both acute angles. So why don't we start with sine of q? So sine of q, opposite over hypotenuse, so that's 3 root 21 over 15. Reducing that, I end up with root 21 over 5. Okay, and then we can plug that into a calculator and see later on if that's 0.4 or not, because right now I have no idea if it is. And then sine of r, we'll do the same exact thing for the other acute angle. So opposite over hypotenuse, so that's 6 over 15. Reducing that, let's see, divide by 3, top and bottom, we get 2/5. Oops, not 5/2, 2/5. Which in fact, this is 0.4. I know that for a fact because if I divide 2.0 by 5, I get 0.4. Okay, so this one is definitely 0.4. Let's check this one out. Square root of 21. Okay, so you have to be careful when you put this in your calculator. I've got square root of 21, and I don't want to put the division sign under the radical because it's the square root of 21, and then I'm dividing that by 5. So you can either press enter here and then divide by 5, or get out of the radical and divide by 5. And that's actually 0.9165, so that one's not going to work. So sine of r is so sine of r is basically the one that's going to give me a ratio that's equivalent to 0.4. Okay, so now we're going to talk about inverse trig ratios. And this is kind of complicated for you guys because you've never really learned about inverse functions. So I'll give you a really quick description of an inverse function. An inverse function undoes its original function. Okay, so you might be given a function and then you'll have an inverse function, and they basically undo each other. When they undo each other, what happens is you get the input all by itself. So you can use inverse functions to solve for inputs of functions. So, for example, sine of q, right, equals square root of 21 over 5. If I wanted to figure out what q was, I'd have to get q by itself. I can't divide by sine because sine is nothing. Sine is nothing without an input. So the only thing I can do is I can use the inverse of sine to get q out. Okay? So that's basically what they're saying here. So these are very important, and we're going to learn these next year and the following year. We're going to use these a lot. Inverse trigonometric ratios can be used to solve for one of the acute angles. So, for example, if I have the inverse tangent, so if I have tan of A equals x, then I know that the tan inverse of x is equal to A. Because basically what I've done is I've taken the inverse of the tan function, which undoes the tan function and just leaves me with the input of A. That's what you're getting right there. And then I do the same, I have to do the same thing to both sides. So let's use an example up here. Let's actually use sine of r equals 0.4. So I know that sine of r is equal to 0.4. Now I want to solve for r. So what is angle r? I can't divide by sine. Sine by itself is nothing. It doesn't exist. Let me prove that to you. If you go in here and you just type in sine and you don't put anything in the input, you get an error. See that error? It's because you did it wrong. Sine always has to have an input. Well, the only way that we can get the input all by itself is if we undo the sine function. And the only way to do that is to do the sine inverse of both sides. Now, sine inverse, the way that we represent inverse is we put like a little -1. So it's the sine inverse. So this means sine inverse. And we do that to both sides. So now sine inverse of sine r basically undoes the sine. These undo each other, and you're just left with the input, which is r. And then on this side, I would go into my calculator. Now, where is the inverse? Let's see, my computer. I got the sun shining here, so it's hard for you guys to probably see me. But, see the sine function? See right above it how it's sine inverse? So you're usually going to use your second function or your shift button, and you're going to hit second or shift sine, and that's sine inverse, and then I would put 0.4, right, for this side, sine inverse of 0.4, and I end up getting 23.578. I'll always round to like the third, at least the third decimal place, unless they tell me otherwise. But that's how I would find angle R. So now this would be true for all of them. So you have an inverse tangent, tan inverse, right? You have an inverse sine, and you have an inverse cosine. So here's an example. I'm just going to put a little highlight here. This is me doing a problem with sine inverse. I'm not going to go through this. This is basically just the ratios. So you basically would do tan inverse of the ratios like I did here. This was the ratio of opposite over hypotenuse. So I did the sine inverse of this. This is them not writing the equation the first time. And I think that what you want to do is you always want to write the equation, the original equation, and then you want to undo whatever's happening to your variable that you're trying to solve for. So this would be the proper way to go. All right, so we have, well, they all have inverses, but you have inverse tangent, inverse sine, and inverse cosine. Those are all on your calculator. Above sine, we got sine inverse. Above cosine, we got cosine inverse. And above tan, we got tan inverse. Sometimes you also see these instead of inverse tan, it'll be arc, A-R-C. But let's not worry too much about that right now. All right. Example 2. Let A, B, and C be acute angles. Use a calculator to approximate the measures of angle A, angle B, and angle C to the nearest tenth of a degree. So they've already written out the ratio for you. So tan of angle A, which is opposite over adjacent, ended up giving us 3.29. So now what we're going to do is we need to solve for A here. We're going to solve for B here, and we're going to solve for C here. Okay, so first one. Tan of A equals 3.29. Well, how do I get A by itself? You can't divide by tan. That's nothing. Okay, it doesn't work. So instead, what we're going to do is we're going to do the tan inverse of both sides. Again, taking the inverse of a function just gives you the input. So on this side, I'm just left with A. And on this side, I'm going to need my calculator. So tan inverse. So I go over here on my calculator. I go tan inverse of 3.29. And it says to the nearest tenth of a degree. So this would be 73.1. So A is approximately 73.1 degrees. Okay, first one. Let's do B. So now I'll do sine of angle B is equal to 0.55. This is the ratio. This is where my B is. It's stuck in that sine function. The only way I can solve for B is to do the sine inverse. So I sine inverse both sides, because what you do on one side has to happen to the other. Taking the inverse of a function undoes that function. You're just left with the input. And then I use my calculator. Sine inverse of 0.55 That's 33.4. We're rounding up there. Degrees. Okay, and then I'm going to do one more. Letter C here. So we've got cosine of C equals 0.87. Once again, I'm trying to get C by itself. It's stuck in the cosine function. The only way that I can undo a cosine function is to use the cosine inverse. And I'll do that for both sides. Taking the inverse of a function undoes that function, and you're left with just the input. And so cosine inverse of 0.87 is what I care about. And I end up with 29.5. Okay, so pretty straightforward. I know right now you're probably thinking to yourself, what the heck is this inverse thing? And I promise next year we'll talk so much more about it. You'll actually be sick of it and wish that we didn't talk about it. It is really important. Just know right now that if you have a function and you want to get the input out of that function, you want to get it all by itself, you have to use the inverse, okay? And right now we're using these with our trig functions, but this will be true of any function out there. You can use this on lines, you can use this on parabolas, you can use this on every function you learn about. So what does it mean to solve a right triangle? Solving a right triangle means to find all unknown parts. So all unknown side lengths and all unknown angle measures. So we're going to find all unknown side lengths and angle measures. So you can see down here in example 3, well, we have two of the side lengths. We have the hypotenuse and one of the legs, but we don't have the third leg, or I should say the second leg. So we don't have the third side, and then we also don't have the two acute angles. So we're going to go ahead and we're going to solve this right triangle by solving for all three of those things. Okay, so first of all, I'm going to need to know this side. Because it's opposite angle C, I'll call this side C. Okay, that's one thing we don't know. We also don't know angle A. That's a question mark. And we also don't know angle C. That's a question mark. Probably the first thing I would do is I would always find the missing side first. That's pretty easy. It's a Pythagorean theorem, right? So basically I can say C squared, which is a leg, plus 24 squared is equal to 25 squared. All right, so I got C squared plus, let's see, what's 24 squared? 576 equals, and 25 squared, I have that one memorized, that's 625. Okay, we'll solve for C squared. Oops. I'll take one more step. So I'll subtract 576 from both sides to do that. I'll show you that work. And 625 minus 576 is 49. That's nice. So then if I take the square root of both sides, C is equal to 7. Okay, so C is done. Actually, I'm going to erase my question mark and put 7 there. Okay, after that, let's see. Now we can solve any of these sides that we want. Okay, and it's totally up to you, any of these angles, the acute angles that we want. It's totally up to you how you'd like to do it. Why don't I go ahead and find angle C? So I can use, I can use cosine, I can use tangent, I can use sine. It doesn't matter. Look, I've got opposite over hypotenuse, which is sine. I've got adjacent over hypotenuse, which is cosine. And I've also got opposite over adjacent, which is tangent. So any of those will totally work. It doesn't really matter. Why don't I do cosine of C, since they start with the same thing? Both start with C. So cosine of C is equal to adjacent over hypotenuse. But I need to get C all by itself. And the only way to do that is to do the inverse of cosine. So if I do that on this side, I have to do it to the other side of the equation taking the inverse of a function undoes that function, so you're just left with the input. And then you have cosine inverse 24 divided by 25, and I end up with 16.2. Oh, it says to the nearest 10, so 16.3. So I'll put approximately 16.3 degrees. All right, so that's the measure of angle C. I'm going to put measure of angle C. That way I can differentiate between C. This is like a lowercase c, but it's not really very obvious. Another thing I like to do is I like to actually write them into the triangle. That way I know when all the pieces have been found. Now from there you have a couple of other options for finding your third angle there, your second acute angle. One of them is you can go ahead and keep using trig functions and go ahead and solve, and you'll have to use the inverse to do that. The other is, what do you know about all three angles in a right triangle? That's right, they add up to 180. So I also know that if I want to find the measure of angle A, it's basically going to be 180 minus the other two angles that I have. One of them is 90, and the other one is approximately 16.3. This is pretty rounded, but it is what it is. So then I can just use my calculator. Actually, that'll be 90, right? 180 minus 90. You can also think of it like that. You could just write 90 and then subtract out that 16.3. But let me go ahead and I'll just do what I have written down here with parentheses. So in my calculator, I can actually subtract all of those parentheses plus 16.3, which is 73.7 degrees. And I'll also write it here. And now when I look at this triangle, I can see that I have all three sides and I have all three angles. And I've also circled my work here, and my answers, I should say.